Hello there, Mr. Sutton here, bringing you the AB Calculus 3-2 Extra Practice Solutions on Differentiability Part 1. To find the domain on this function, we're looking for, let's look for places first where the domain does not exist. So we'd be looking for open dots that don't have a solid dot to fill them in. So we're starting at 1 on the left, ending at 6 on the right. Those are our endpoints. And the only trouble spots are these two spots right here at 2 and 4. But we notice there are solid dots to replace those open dots that are missing. So the domain is actually everything between 1 and 6, including 1 and 6. To figure out intervals of continuity for this one, let's start by finding discontinuities. So we notice there's one here at x equals 2, a removable discontinuity there. We also have a jump discontinuity at x equals 4. And that's it. So we're going to be continuous everywhere except those spots. So from 1 to 2, and also from 2 to 4, and then finally we have an interval from 4 to 6. To find the places where this function is differentiable, let's find the places where it isn't. We have a discontinuity at x equals 2 and also x equals 4. We saw those on part B. And then we have a cusp, or is it a corner? Well, it looks like a cusp if you come from the right here, at x equals 3. So those are our only trouble spots. So we're going to be differentiable from 1 to 2, from 2 to 3, 3 to 4, and then finally from 4 to 6. For this problem, to figure out places where the domain exists here, we're basically looking at all the places where this function is defined, so solid dots and solid lines. That's going to be everywhere between -3 and +3. Figuring out where this function is continuous, let's first look for discontinuities. There are none. There's no breaks or holes in the graph, so we are continuous everywhere from -3 to 3. To figure out intervals of differentiability on this, let's find places where we are not differentiable. There are no discontinuities, so we're only going to be looking for cusps and vertical tangents. We see that we have a cusp at what appears to be -2 and also +2, and that's about it. So we're going to be differentiable from -3 to -2, where we hit that first cusp, from -2 all the way to +2, and then from the cusp at 2 to the endpoint at 3. To figure out the domain on this function, let's look for open dots that aren't replaced by solid dots and leave those out of the domain. Now the only trouble spot for domain is this spot at -1, but we see we have a solid dot there even though we also have these open dots. So we're actually the function exists everywhere from -infinity to +infinity. To figure out intervals of continuity for this, let's look for discontinuities first. We see there's only one discontinuity. We have a jump at x equals -1 right here. So we're just going to write our intervals around that. I have an interval from -infinity to the jump at -1, and then we'll do a union from 1 to +infinity. To figure out where this function's differentiable, let's find the trouble spots first and leave those out. So we have that discontinuity we saw in part B at -1. We also have a cusp at x equals 2, and that looks like about it. So we're going to be differentiable from -infinity to -1, from -1 to +2, and from 2 to infinity. For number 5, we're analyzing this function. Let's do domain first. So let's see, going from left to right, there's an open dot, but there's a solid dot there to make up for it. Here's another solid dot. Let's see, we don't really have any openings in the graph until this asymptote at x equals 3. So our domain then is going to be -infinity to -3, or rather +3, comma 3 to +infinity. And then for continuity, we have a jump discontinuity at x equals -1, a removable at 0, an infinite discontinuity at 3, and it looks like that's it. So our continuity then goes from -infinity to -1, -1 to 0, 0 to 3, and 3 to infinity. And then finally, for differentiability, going pretty much from left to right, at -2 we encounter a cusp or a corner. At -1 and 0, we already talked about those discontinuities that mess up differentiability as well. 1 is a cusp, so is 2 for that matter. and then we have a discontinuity at 3. And I think that's it. That's pretty much every integral value on the graph, though. So our intervals of differentiability, then, we're going from negative infinity to negative 2, negative 2 to negative 1, negative 1 to 0, 0 to 1, 1 to 2, 2 to 3, and 3 to infinity. On this problem, we're given this piecewise function of f, and we're asked which of these statements has to be true. So first one, f prime of negative 4 equals 2. So we're talking about the slope at x equals negative 4. Let's look at the graph. So here is x equals negative 4 right here. They're saying that that slope is going to be 2. And it looks like at this spot we're going up 1 and over 2. So since our slope of f is 2 at x equals negative 4, this is a true statement. And anything that does not have 1 in it can be eliminated, like choices B and D. All right. So let's take a look at the next one, statement 2. F prime is negative on the interval negative 1 to 1 and 2 to infinity. Well, from negative 1 to 1, our f function is decreasing. Same thing on the interval from 2 to infinity. Since f is decreasing on these intervals, its derivative, f prime, is certainly going to be negative on those. So that's a yes for that statement. So we can then eliminate choice A, because that only had statement 1 in it. Now statement 3, f of x is continuous at x equals 1, but not differentiable there. Well, at x equals 1, we have a corner here. Since we have a corner, we're going to be continuous, but definitely not differentiable, because we have an abrupt change in slope. So that's also a yes. So then statements 1, 2, and 3 are all true for choice E. On this problem, we're given the graph of f, and we want to know which of these statements is going to be defined and continuous, but not differentiable. Okay, so let's take a look at one here. That's x equals 2. So at x equals 2, we have a removable discontinuity. So we're definitely going to be defined there. We're not going to be continuous, though, and because we're not continuous, we're not going to be differentiable. So this is going to be eliminated from our answer choices. So anything with 1 in it is no good. So choice B and D are gone. Looking at 2 here, this is x equals 3. So at x equals 3, we have what appears to be possibly a cusp or a corner. So we're going to be continuous at that, but not differentiable, because we have an abrupt change in slope. So this is going to be one of our answers now that we want to include. So it could be A, it could be C, it can't be D, so it's either A or C. Can't be E. All right, so it's all down to statement 3. X equals 5, continuous but not differentiable. At x equals 5, we have a smooth turnaround. We're definitely continuous there, and we're also differentiable. The derivative there we know is just going to be 0. So because of that, choice 3 is no good because it is differentiable there. So only choice 2 then, statement 2, option 2, which means we have to pick answer choice A that has 2 only. For this problem, we have a graph of f, and they're telling us that we have a vertical tangent at the point 2, 0, and horizontal tangents at, let's see, 1, negative 1, and 3, 1. For what values between negative 2 and 4 is f not differentiable? Okay, so let's look for non-differentiable spots. We're looking for discontinuities, cusps and corners, and vertical tangents. We have a discontinuity that we see pretty clearly here at x equals 0, a jump discontinuity. And although it's hard to read it off a graph to tell if it's just a vertical tangent or just really steep, they came out and told us we had a vertical tangent at x equals 2 right here. And there's no other spots that are not differentiable. The smooth turnarounds they were telling us about, the horizontal tangents, the derivative does exist there. It's 0, so we don't have to worry about those. It's only then x equals 0 and 2 where we are not differentiable. So that's going to be choice B. On this problem, we want to know which of these 3 statements, if true, could be used to conclude that f of 2 exists. So we have the limit as x approaches 2 existing, we have continuity at 2, we have differentiability at 2. Well, we know at least one of these has got to be true because the answer choices don't have a none of the above. All right, so let's look at the first one, limit existing. Is that enough to prove that f of 2 exists? It is not, because we know that the limit can exist if there is a hole. You're still approaching the same place from both sides, even if there's nothing actually defined there. So the limit itself is not enough to prove that f of 2 exists. All right, how about continuity? Well, f of 2 existing is a condition of f being continuous at x equals 2. So that means that if we know we are continuous, then we have to have f of 2 existing. Otherwise, we could not have proven continuity. So this is a yes. And now the last condition, f is differentiable at x equals 2. Well, continuity is a condition of differentiability. If your function's differentiable, that means it must also be continuous, which again means that the function must actually exist at the spot of continuity. So this is also a yes then. So then we needed options 2 and 3, which is choice C. For this problem, we're given the graph of f here, and we're told that we have a vertical tangent at x equals -2 and horizontal tangents at x equals -3 and -1. So we want to pick out the statement out of these four that is false. So be careful on this one. So choice A, f is not differentiable at -2 because the graph has a vertical tangent there. Well, that is true. There is a vertical tangent there. I mean, they told us. But also, that is a reason for non-differentiability. You have an infinite slope. So that's a true statement, and it's not the answer choice, therefore, that we wanted. Choice B, f is not differentiable at 0 and 2.5 because f is not continuous. Non-continuity is another way to have non-differentiability, so this is also true. F is not, so choice C now, f is not differentiable at 1.5 and 4 because the graph has sharp corners. Well, yes, there's a cusp at 1.5, or actually a corner at 1.5 and a cusp, if we're being really specific here, at x equals 4. That means you're not going to have differentiability. With the cusp, I mean, one of the issues, both of the issues are you have an abrupt change in slope, and the cusp has infinity thrown in as well. So this is a true statement, not differentiable at those spots. So that means choice D has got to be the answer, but just looking at it, f is not differentiable at -3 and -1 because we have horizontal tangents there. Well, not differentiable means you can't take the derivative, means the derivative is not a constant. But if you look at those spots, the derivative, the vertical, or the tangent line to those spots is going to be 0. That's a horizontal tangent line. So that means that f prime would have a value, would be 0, which means that we are differentiable at horizontal tangents. So this is a false statement, and it's the one we need to choose then, choice D.